In this lesson, we'll implement the Harry Markowitz mean variance framework with our programming. First, we'll recap the mean variance framework. Subsequently, we'll discuss the tail risk measures, namely value at risk, that is VAR, conditional value at risk, CBAR, and expected shortfall, ES. Next, we'll download securities data from Yahoo Finance. Then we'll compute returns and visualize various properties of this data. Next, we'll initiate a portfolio object, formulate various portfolio constraints, including box, group, and risk budget constraints. We'll formulate and visualize portfolios with different tail risk objectives. This includes equal weighted portfolios, minimum risk portfolio with a target return, tangency portfolio, and global minimum risk portfolio. Next, we'll construct efficient frontier in an interactive and customized manner and visualize it. We'll also initiate a short portfolio object and identify portfolios with different risk return objectives. Lastly, we'll also understand how to set up a portfolio in mean CBAR, that is conditional value at risk framework. In this video, we'll recap our discussion on mean variance framework. Recall the discussion with video topic on portfolio optimization. We started with 4 securities A, B, C, and D, and we kept forming different combinations of these securities A, B, C, and D. And as we keep on doing that in a return and standard deviation space, we obtain what is called feasible region. This blue region is the feasible region, which represents all possible combinations of return and risk, that is standard deviation. This feasible region is represented by this Eckert kind of shape, and each point here represents a combination of risk and return that is available to investors in the form of portfolios. Now, how do we improve our position in this feasible region? We can either go up or we can move left. And as we keep on doing that, we reach a particular surface or the surface of this Eckert region. This surface of Eckert region, this surface is called efficient frontier because every point on this surface represents a unique combination of risk and return, which can be explained in the following terms. For example, let's take this point Z. Now, for a given amount of return, this Z would obtain minimum risk, or for a given amount of risk, this Z would give you highest return. In a sense, every point on this surface obtains or achieves a very important, or we can call best combination of risk and return. That is, no other portfolio for a given amount of risk can offer you higher return, or for a given amount of return can offer you a lower risk, and therefore this is called efficient frontier given this property of portfolios lying on this surface. While we cannot directly compare these portfolios on this surface per se, individual investors, depending upon their degree of risk tolerance or risk averse nature, they will choose a given particular point on this surface. For example, an investor who is slightly willing to take more risk would probably prefer a position here, and therefore he would also be rewarded by a higher level of return. However, in contrast, an investor who is not so risk taking, probably more risk averse, and would like to take a position here, and therefore would be rewarded with this amount of expected return. In this backdrop, 2 points are very important, which is one is this S and one is this S dash. Because this point S offers the lowest amount of risk. This is the lowest amount of risk available across the entire feasible region. So any portfolio in this feasible region does not have lower risk as compared to S. So this point S is also called global minimum variance portfolio because it offers you the lowest variance across all the available feasible portfolios. Please notice this term feasible portfolio. Feasible portfolios are all the portfolio set that are possible within this feasible region. Another portfolio S dash is important because it offers you the highest return across the feasible region. So any portfolio, if you take any portfolio in this feasible region, S dash offers you the highest return. And the surface, this efficient frontier represented by SS dash, is a unique and best combination of risk return profile in the feasible region. And that is why we also call this efficient frontier, this SS dash region. Also, while discussing this portfolio optimization scheme and efficient frontier, we noted that if risk-free lending and borrowing rates are available, which are same, then one can also draw a tangent from RF to this efficient frontier. And this tangent line will touch, let's say, at point S. Then this S portfolio becomes one of the best optimum portfolio, and a new set of efficient portfolios will emerge, which comprise the line joining RF to S. We also noted that on the left of this RF segment, RF to S, this is called lending segment because any point on this portfolio which represents a combination of available risk and return, which is RF joining S, RF to S, can be obtained by mixing some amount of wealth in RF and remaining amount of wealth in S. Let's say if you are investing 40% in RF and remaining 60% in S, then you can obtain this portfolio segment which is called lending. We also noted that on the right of point S, there is a borrowing segment which one can obtain by borrowing at RF, because we said RF is available for both borrowing and lending, and therefore a slightly more risk-taking investor who is less risk averse can borrow at RF and invest his own wealth at RS at this S portfolio, or the most optimum tangency portfolio, what we call, and remaining borrowed amount as well into S to obtain a position on this borrowing segment. And that is how this new efficient frontier is arrived. Importantly, this is also called two portfolio theorem or separation theorem, because now we need to only identify two portfolios, that is RF and the tangency portfolio S, to offer a wide range of risk return profiles, or what we call the new efficient frontier represented by this straight line. Also, now irrespective of investors or our clients risk profile, whether they are slightly more risk taking, less risk averse or more risk averse, we only need these two portfolios RF and S to offer them a combination or a choice or a portfolio of their taste and preferences that is desirable to them. So we have separated the decision of this portfolio RF and S from the investor's risk preference. That is why it is also called separation theorem or two fund theorem. To summarize, we recap our discussion on efficient frontier and mean variance framework. We also noted that mean variance framework employs variance or standard deviation as a risk measure. However, there are two very important risk measures that we also employ. One is called value at risk and another is called conditional VAR or conditional value at risk, or often referred to as expected shortfall measure, that we are going to discuss in the next two videos. In this video, we'll discuss a very important measure of tail risk, that is value at risk based models. If you are asked on any given day what is the probability that you can lose more than $10 million, then as a first step you'll try to plot your returns from negative returns to positive returns. These are your losses or these are your gains. And then also on the vertical axis you have frequency or probability density of returns. Often it is said that this kind of graph can be very nicely represented by normal or standard normal distribution. If you are using standard normal distribution, then on x-axis you have what we call z values or units in terms of standard deviations. This is a very effective way of representing the probability density distribution of variable like return. Let's say you plot this kind of graph and you find that at 5% cutoff, you start from this end to this end, and you find that 5% area stops or cuts off at a value of 10 million loss. Here, this point represents $10 million loss and the area under the curve is 5%. So 5% probability lies with a minimum value of 10 million. Then you say that assuming this was a daily distribution, then you can say on any given day your loss can be more than 10 million has a probability of 5%. Either it can be presented in terms of absolute value or also in terms of return form, that is X percentage, talking about negative returns or losses. So there are two ways to express this phenomena. One, you can either say that there is a 95% probability that your maximum loss is $10 million, or there is extreme 5% possibility, possibility that your loss can be more than $10 million. So these are two ways to express the same thing. And in that case, it is said that your 5% daily VAR is $10 million. There can be a parallel negative return in the form like X% or losses that can also be expressed in VAR form. So let's say this 10 million VAR was X%, then you would have said that your 5% daily VAR is X%, which is negative losses or negative returns. Before I elaborate this formula in detail, please note that there are three important inputs to specify VAR. First, there is a time period. In the previous case, we noted daily period. It may be weekly or monthly as well. Second, the level of confidence, that is 95% or 99%. In that case, if confidence is 95%, then that alpha value, in the previous case, it was 5%. And if you take a confidence level of 99, then by the same logic, your tail probability that you are examining will be 1%. That is 1 minus alpha will be 99%, then alpha will be 1%. And lastly, the estimate of loss in absolute terms, this estimate of loss, which was $10 million in absolute term or in percentages term. Now, from our knowledge of standard normal distribution tables, we already know that at this point is supposed to be 5% tail, the 5% probability. Then this line is 1.645 standard deviation on the left. We can identify this point as 1.645 Z value. So Z value equal to 1.645 on the left side will correspond to that 95% region. That means area on the left side is 5% and on the right side is 95%. Now let's come to this formula. What does this formula mean? This formula is quite simple. It indicates the VAR value for a given distribution of returns. Let's say you want to have this alpha value or value of significance as 5%. Then the VAR value is defined as if we plot the return distribution for that given frequency, which is daily or weekly, the 5 percentile or 5% quantile, or you can say 5 percentile region, the minimum value in this region is the VAR value. Now, if you have plotted the probability density of return distribution, let's say, and you have identified this 5% probability region, the minimum percentile value will of course be that particular quantile or percentile. For example, we are talking about 5 percentile. That means the minimum value will correspond to exactly this 5 percentile cutoff point. This is what is represented by this formula, that the minimum value for a given chosen value of alpha percentile or quantile, let's say you're talking about 5 percentile, then the cutoff value is the minimum value of Z that corresponds to this cutoff. So which is nothing but simply the percentile value corresponding to the 5 percentile or alpha level. Now there are two ways to estimate this number. First is if you know the probability distribution. For example, if you believe that your variable or return follows normal distribution and you can plot them around in the form of normal or standard normal distribution, then in that case you can simply integrate over this region. For example, if I want 10% VAR, daily VAR, 10% daily VAR, then I can find a cutoff point on the left of which the area, because we are talking about probability density curve, then we can say the area under the curve is 10% of the overall area. And in that case, that integrated number, because we want area under the curve, that integrated part will represent the area, the cumulative area, the corresponding cutoff point Z corresponding to this 10% area will become my VAR value. So I can identify this Z value here, and this Z is nothing but returns in standardized form. So corresponding to each Z value, there is a particular return value which would be negative because this is the loss region on the left of 0. So we can identify that loss return, and that will be our daily VAR with that particular 90% confidence or 10% significance, or we can say 10% VAR, daily VAR is this value. It can be daily, weekly, monthly, depending upon the distribution of returns that is being examined. The second and empirical way is to have return data, distribution data. We can order this and start examining from the negative side, negative return, or the lower side. And let's say if you are looking for 5% VAR, then you can cut off the extreme negative 5, extreme lowest 5% observations. You can cut off, let's say you have set of observations, you can put a cutoff line, and on the left of this cutoff line you have 5% observations. Then the cutoff point, the maximum return in this cutoff point becomes your VAR. In terms of magnitude, this will be the lowest value on the negative side, but in terms of signed value, it will be the maximum. And this will become our VAR. For example, let's say your values on the negative side are -5%, -4%, -3%, -2%, and -1%. Now, please note, in terms of magnitude, this 1% is the lowest. However, in terms of signed value, this is the highest, and this value, once we cut off at this level and we have these 5 values left, then this -1%, which is the highest, or in terms of magnitude, the lowest value, will become my VAR value. So we need to order our return observations and take the one which is highest in terms of magnitude, or lowest in terms of magnitude, and highest in terms of signed value. Mostly chances are it will be negative. So generally returns are symmetrically, to some extent they are symmetrically distributed. So you have negative as well as positive returns. So if you are ordering them from the lowest side, chances are that on extreme 5% or 10% you will have negative returns like this. This value at risk measure is very often employed by banks to estimate the performance of their portfolios and possibility of extreme loss events. To summarize, in this video we discussed the concept of value at risk and how it is helpful in estimating the tail risk of a security or a portfolio. However, we noted that there can be instances that can and obviously will go beyond, and extreme loss events that are beyond this VAR level, and therefore we need a slightly more accurate and efficient measure to handle those situations that are extreme situations and goes beyond this value at risk measure. In the next video, we'll discuss that one such measure, which is called conditional VAR or CVAR or expected loss. In this video, we'll introduce a very important measure of tail risk, that is conditional VAR, CVAR or expected shortfall measure. VAR method, value at risk method, that we discussed in the previous video, considers all the possibilities with a given certain confidence interval. For example, we said we are 95% confident or 99% confident. However, there are scenarios when this position is exposed to those losses that are beyond these levels of 95 or 99% confidence. And in order to cover this exposure that may happen in those extreme events, a more advanced version of risk measure, that is conditional VAR or CVAR, often referred to as expected shortfall, is proposed. The measure computes those losses, expected losses, given that this confidence level of 95% is reached. For example, given that you are in this extreme region, given that you are in this region, what is your expectation of losses? Let's say this is 99%, or if you believe 95%, then this region, if it is 95% cutoff, then what is your expected loss if you are in this region or this confidence level is breached? In order to answer this question that we are talking about extreme event case, what is the expected value of loss? To answer this question, what we do here is we plot our returns on the opposite side. In contrast to our earlier plot where we had negative returns here and positive here, we essentially plot the losses, that means negative returns. So this will be our positive side, and these extreme scenarios will represent those extreme negative returns or losses. Now, objective here is to compute the expected or average or mean value of losses given that these events were to happen or occur. Let's take a simple case. Let's say you have 3 possible scenarios. Given that this scenario is breached, that is conditional sort of base probability that this extreme limit, alpha, it can be 5%, that means 95% confidence level, or 99% confidence level is alpha is 1%. This level is breached and we are talking about this region. Condition on that a priori probability is given that this region is breached. You have 3 possible scenarios. P1 probability, let's say 10%, that loss is 5 million. let's say I'm putting negative sign for loss, and another 10% probability that loss may be 10 million, and 80% probability that loss may be 1 million. Then my expected loss, given that these are the only three possibilities, given that my losses exceed this level, then P1 into this minus 5, P2 that is 10% into 10 and 80% into 1 will be my resulting number. This is my 0.8, then this is 10 million, so 1, and then 10% with 5, so 0.5. So overall my losses are 2.1 plus 1, 0.5 plus 0.8, that is 2.3 million losses. So these are my 2.3 million losses, given that the losses exceed this level. So this is why this is conditional VAR, because condition that this VAR level is breached. So condition to that, what are my expectation of losses? Now this was a rather simple case for discrete events, and therefore it can be represented very simply like this, that condition, this is the conditional operator, condition that x is greater than var, that means my var level is breached, that is my given condition. What is the expected value of x, and which we simply computed as p1 x1 plus p2 x2 and so on. If your returns are in continuous form, or you believe that returns follow some kind of continuous distribution, then also the case is not too difficult. You have continuous value of return observations, you can plot them, and for each return observation there is a small probability density value that this return observation will materialize, or if you're talking about in terms of loss, then x value along with their probability density. And then you can integrate, this is 1 minus alpha region, please remember this is 1 minus alpha region, which is your critical region, your confidence level. Let's say here, if you're talking about confidence, let's say alpha, we are denoting slightly in a different way. Let's say my alpha is my confidence of 95%. So if this region is 95%, this remaining tail region of 5%, which is 1 minus 0.95, this 5% region, I will integrate from this 1 minus alpha point to 1. So I'll integrate from 1 minus alpha to 1. I'll integrate this x value, and df is my probability density, which will also a function of x. So I'll integrate x df, where f is a function of x, starting from this 1 minus alpha point, assuming that this alpha was my confidence interval. So from this 1 minus alpha to 1, if I integrate, I'll essentially get this probability, which is my expected value of loss, given that the value has exceeded this var level, and it will be something like 1 minus alpha to 1 integrate x dfx. To summarize this video, we noted that CBAR method accounts for extreme scenarios that are not captured by var levels. For continuous distributions, the area under the tail segment, as we noted, which is essentially the loss segment, which was obtained through integration, is a very accurate measure of that expected shortfall or conditional CVAR measure. For discrete observations also, we noted that P1 x1 plus P2 x2 kind of probability weighted expectations can be employed to compute CVAR. Given that the var levels has exceeded, the a priori probabilities of these extreme losses P1, P2, P3 and so on can be multiplied by these extreme loss events x1, x2, x3, and these probability weighted expectations are used to compute our conditional VAR. As we start our journey of portfolio construction and its implementation with our programming, in this video we'll begin with downloading data from a very powerful and publicly available data source, that is Yahoo Finance. We'll start with downloading the securities. First, we'll download the relevant packages, starting from library command f portfolio, that is the most important package for this. Then we have library tidyverse, and we'll keep these packages loaded for times to come, so that whenever we are running a function related to portfolio construction or portfolio optimization, we are able to run those. Another important package, the library zoo. We have library quant mode. Now that we have loaded the relevant packages, we'll start with the downloading securities. As a sample, let me show you. If I download a single security, I need to know, and please remember, I need to know the ticker on Yahoo Finance in order to download the security. I already know that Amazon has a ticker AMZN, so I'll use this get symbols command. I'll use this get symbols command and this symbols. I need to provide the symbol that I want to download, which is Amazon. Now here I am downloading a single security. I am downloading all the data in this AMZN object, and I'll put this command auto.assign. I'll put this command auto.assign equal to F, and I'll supply the period also from maybe 2010 1st of Jan. So this is my starting period, and I'll provide this data to 2021 December 31st. So this is my closing period. Now when I run this command, notice when I run this command, Amazon object is created on my environment. So when I run this command, notice as this command is run, data from Yahoo Finance is loaded. Let me see. Let us examine this object. So we have the following data, which is open, high, low, close, volume, and adjusted price is loaded. So we'll use this adjusted price series, which include any adjustment for dividend and other cash flows. So we'll use this Amazon.adjusted pricing. Let us examine the class of this object. So this is XTS or zoo kind of object that is downloaded. Now please remember, in order to construct portfolio, we need to download multiple objects. So for that, again, similar code is used. Let's call this multiple series object as DF or data frame. I'll use the same command with same symbols, get symbol. This get symbols command I'll use. But this time around, I'll provide a number of symbols because we need multiple stocks to construct our portfolio. So first, this symbol, this is for Nifty 50, NSCI, this is for Nifty 50. And I'll provide it in vector form. Next, we have this JSPC. This is for S&P 500. Later, I'll specify their more accurate names to avoid any confusion. Then we have FCHI, which is for CAC 40, major index in France. It's a major national index. Then you have GDAX-I. This is for DAX Germany, major market index in Germany. Then you have FTSE. This is for FTSE 100 in UK. Next you have stocks, which is major Euro stocks index. And then you have Russell, which is another Russell 2000, which is another major index. For this, which we have RUT. So these are the major indices that we have signed. Now, interestingly, in this particular command where I'm loading multiple securities, I'll not use auto.assign as false. I'll set auto.assign as true. So all the symbols will be separately loaded in separate objects, not assigned to this DF. And I'll use the same time window. The time window I'll keep as same, which I used earlier. And now I'll load this. Notice when I run this command, in my data environment, all the objects are loaded separately, and each object contains the data. And now I need to combine the entire data object. So I need to use the tickers by the name they are loaded. Ticker, let's call them tickers. And I'll use these tickers as list objects, combine them. First is NSCI, Then I have JSPC. These names are the names by which they are loaded in my environment. I'll change them to more suitable names shortly. GDEX, FTSE. So these are my objects. I'm using major market in D6. These are generally less noisy, so portfolio construction is expected to be smooth without any hassles of thin trading, issues related to thin trading and so on. So now I'll run this command and load and create a this object tickers, which is a list object. I'll merge, and this ticker, if I print this ticker object, notice it carries the consolidated thing. From this consolidated thing, I'll merge. These are all in the list form. So each object is contained individually. So I'll bind them together. Let's create a new data frame df1, which will essentially bind all the objects. Let's use this merge command to bind them. It will bind all the objects. Once I have bind it in df1, notice a large extensible time series XTS object. I'll select only adjusted prices. And how do I select only adjusted prices? It's quite simple. I'll use this final let's call it final underscore df, where I'll filter the df underscore 1 series, which is my combined consolidated series. I'll use this string detect command, and in this string detect function, I'll supply the column names of this df1 object, and I compare it with the term adjusted. Those columns or variables where this adjusted term is there, they will be selected and remaining will be ignored. And if I have done it correctly, let me look at final dot underscore df object, and let's see what kind of columns are there. Notice all the indices, only their adjusted prices, the column with the adjusted prices are appropriately selected. So this is my final data. To summarize this video, we loaded the relevant packages of F portfolio, Tidyverse, Zoo and Quant Mode. Then we demonstrated how to download data for Yahoo Finance using a single security, that is Amazon. After that, we downloaded a number of securities from Yahoo Finance, that is Nifty 50, S&P 500, CAC 40 from Paris, DAX Germany, FTSE 100 from UK, stocks from Euro, and Russell 2000. And then we combined them, extracted their adjusted prices in our consolidated data frame format, which is final underscore df. And this will be further used in the subsequent processing and return computation. In the next video, we'll compute the returns and we'll try to visualize the data. Now that we have downloaded the data, let us start by properly naming it, naming the variables or the security prices, and then computing returns and subsequently visualizing it. So as a first step, we will give appropriate names to the column. So we'll name, compute returns, and visualize. So as a first step, let me just give the names with this call names command. Here I'll use final underscore df. This was our original data that we downloaded, but we give it appropriate names. The first name is Nifty. So since we downloaded Nifty 50 data, I'm giving it a name Nifty. Then S&P 500. So let me put it as SP, or more appropriately S&P. Next column is CAC. Then DAX. Then FTSE. Next we have stocks, Euro stocks for stocks. Then Russell 2000. Let me call it RUT, that is Russell 2000. So this is my final variable. Let me name these. And if you want to check whether names have been appropriately given, you can again type final underscore df, and you'll find that if I enlarge my console window, you can notice the names that I have given are here visible. As a next step, let me compute the returns, and a very simple and interesting command. Let me call the new data as final underscore df underscore ret. So this command will compute returns, and it's very simple. Diff log. This is a very simple command. It takes the first difference of the series in the log form, which is essentially log returns. This is very easy to do. Those of us who have computed return in the past So those of us who have computed returns in the past, they will know that this command will first create the log of the price series and then take the difference, which is sort of returns in the continuous form. And now that we have this return variable available with us, let's see the head of this final underscore diff object that we have created. Let's see the head of this object. Yes, the returns are computed. The first object is obviously NA because we use the first price series. There is no previous price, so the first prices are NA. We can, in fact, to avoid any kind of trouble, we can just type this command and we'll use this na.omit to remove NAs from this object. So I'll remove the NAs from this object. Now NAs are removed. Also, this F portfolio object or library that we installed, it generally works well with the time series objects. There's a certain time series format that it's most suitable. So we'll run this time series command. And with this time series command, we'll convert our final dfret object to essentially to this final return object. So let me name it as final ret in fact. So this is my final return object that I'll be using. So now that we have downloaded and combined our data into final return form, let us start with a little bit visualization of the data. So we'll visualize the data now. To summarize, in this video, we gave the names to variables. So we appropriately named the variables with their proper security names, and then using diff log command, we computed the returns, and then we removed NA observations, and then we converted our return object to a more suitable time series object. In the next video, we'll try to visualize data and see its properties. In this video, we'll try to visualize the data. So we'll try to visualize the data. Let us start with a simple visualization command, which is plot.xts, and we'll supply this function plot.xts our final data frame, which is final underscore df. This data contains prices. We'll supply, since we have 7 price series, 7 indices, we'll use 7 colors. So this command will ensure that there are 7 colors, 1 to 7. Then central heading is all prices because we are using price series, and then we'll keep the y-axis as empty. So now I can run this command. Notice that once I run this command, I get all the price series on my chart. I can see all the prices. Also, you may want to plot all the series individually rather than putting them in single plot, so that you can make a more appropriate comparison and see their variation properly. So for that, you can slightly tweak the command. For example, you can type plot.zoo and then supply the same object final underscore df. You can again supply all the different colors since we want to plot all the prices in different colors. Again, we'll put the central heading as all price, but this time we'll specify that plot.type is to be plotted in multiple windows. So we'll specify this multiple argument so that plotting is done with multiple windows. Also, we'll keep the y-axis as empty, and then we can use this 6.main argument to increase the size of central heading. Probably a larger central heading will plot. Notice now all the prices are plotted with different colors and different plot windows. You can see their movement more clearly than on the single plot. They are all visible. You can zoom it also. You can zoom the prices and see it. Sometimes you may be not very sure that which window plots which color or which window plots which series. So you can remove this y-lab which was empty, and now if I run this command, now this command is run where I have not specified the y-axis, so the original name from the series will be picked up. Let me just enlarge the plotting window so that we can see the graph appropriately. So if I run this command, notice that now the name of the axis that I specified earlier is also provided. So for example, Nifty is the black one, S&P in the slightly reddish color, CAC is green, and so on. For example, Russell is in sort of brown yellowish color. So we have all the indices that we can identify individually, in fact, on all the 7 indices individually on the graphs. Let's try to plot returns now. We'll make use of same commands. It's quite easy. So now it would be more appropriate to plot the return diagrams, return graphs on separate windows, because return is very fluctuating around mean of 0. It generally it is very fluctuating, so it would be appropriate if we plot them on separate plots. So again, I'll use the plot dot zoo, but I'll supply the final return argument. Here we have the returns, all the returns available. Again, all the 7 will be plotted in different colors. Central heading is all returns because this graph carries returns. We'll specify the plot type, plot dot type as multiple, so that they are plotted in multiple windows. And I'll not specify the y-axis, so that each plot has its own index or return name. I'll just specify that sex.main equal to 3, so that slightly larger graph is produced. So now let me enlarge the plot window before I run the command. So sufficiently I've enlarged it. Now once I run it, notice all the individual indices are plotted and we can see the fluctuations. In fact, we can see around 2000, around somewhere around after 2000, there's a large jump. We can see here this large jump, and this is common to all, and in between also the fluctuations happen because these are broad market wide indices. So whenever there's some kind of global crisis, there would be some kind of co-movement, high volatility and falling prices, which is what we are seeing here, and all the indices are plotted in different colors. Also, a slight modification in the command: if I remove this zoo, notice if I remove this zoo, now the dates are plotted. So I can now I have all the individual indices and their dates are also available with me, so I can identify these fluctuations, their timings. You can see there these timings are around somewhere around 2020. There's a sharp increase in volatility, particularly the down, which is also associated with falling negative returns. So we can say this is probably around COVID period, and it is common to all the indices. As a last step, when you are summarizing the data, you have already plotted it, you have visualized it. As a last step, it is always advised to create a summary measure. So just summarize your data by typing summary and supplying your final return object. So it's nice that it will give you the final summary thing. You can see that summary of all the returns is provided here, nicely printed summary. You have start and end date of the record, and you have Nifty, S&P, the summary returns are also provided. Nicely printed summary. We can see that extreme negative returns are always mostly dominating the returns. Mostly these series are negatively skewed as it appears. To summarize this video, we plotted the security prices together in a single graph. Then we also plotted them in separate graphs. Then we plotted the returns. We can see that returns are negatively skewed, especially during the COVID time. There was large fluctuation and negative returns. This we confirmed with the summary measure. We summarized the returns and saw their distribution: minimum, maximum, mean, median, first and third quantiles. We observed extremely negative returns are slightly dominating, so the return appear to be skewed. We'll conclude with the visualization in the next video, where we'll examine the density distribution of all the returns. In the previous video, we visualized the price and returns plot. In this video, we'll create density plots to examine the distribution of the data. As a first step, we create the main plot of density. So first we'll create the main plot of density. This we'll do for Nifty. So Nifty will be our first stop, where we'll create the density plot. We'll give the main heading as density plot. Also, we'll specify the color as 1. I'll give the color in sequence of 1 to 7. There are 7 securities. Next, based on my experience, I know the nature of plots, so I'll specify the x limits from minus 0.1 to 0.1, so they remain actually aesthetic, and y limit as 0 to around 70. So the some of the peaked security densities are also fairly plotted, and a line width of 2. So this will be my first plot. Let's see if it has worked. It seems to have worked. In addition to this, I'll create other plots, but I'll not create fresh plot. I'll use lines command to create new plots in the same plotting window. Let's see how to do that. So I'll remove my main plot heading. So this is not required. I'll just need to change the name of the security. This time it will be S&P 500. I'll change the color to 2. So color coding scheme as 2. And I need not specify X limit and Y limits, that I have already done. I only need to specify the line width as 2. So let me clean the code. Now for next lines, I just need to change the name of the security. Let's say S&P to CAC, color as 3. For next security, again from CAC to DAX, color as 4. From DAX to FTSE, color as 5. From FTSE, I'll shift to stocks, color as 6. So I'm just changing the color scheme. And lastly, from stocks to Russell 2000 and color as 7. So now these are my line plots for which I'll just add in the main diagram. Notice all those plots are plotted. In fact, the red one is extremely peaked. Now you also need to add some kind of legend to make distinction between different plots. So it seems the top left window is slightly open. So I'll use top left window to add the legend. And I'll use a small trick. I'll not explicitly enter the names, but I'll use this call names command and extract the name from the return object itself. Lastly, since I'm using the color coding from 1 to 7, I'll continue to do the same, and then I'll add the legend. So notice nicely legends are added. Probably I'll enlarge the plot window and then recreate this plot for better comprehension. So now it looks better. Let's re-examine the plot. So I'll zoom it. Notice all the plots in different colors. For Nifty in black, S&P is more reddish, CAC is green, and they are plotted together. In fact, the red one seems S&P is slightly more peaked. Nifty is not so peaked, while Russell is much lower in terms of peak. However, if you look at the overall nature of these graphs, it seems that broadly there can be a normal curve that can be superimposed on these. They appear to be fairly bell-shaped and normal distribution, and that is the reason earlier, when, if you recall our discussion on normal distribution video topic, we discussed in great detail how normal distribution is extremely useful for modeling such return behavior, and we can see that here manifesting itself. We can see how normal distribution nicely fits or appears very similar to these security distribution density plots. To summarize, in this video, we plotted the density distributions of all the 7 security prices, and we find them very similar to normal distribution. In this video, we'll learn how to initiate a simple portfolio object. So we'll initiate and interpret a simple portfolio object. For example, I can simply create a simple portfolio object with default specifications. Let's call it default spec by just writing this portfolio spec function. I can nicely print the contents of this default spec object by just typing default spec and printed it in the console. I can print the output. The function portfolio spec here allows us to define the specification settings from scratch. The default setting, as we can see here, MV, mean variance, the default settings are for a mean variance portfolio. We can easily see the arguments for this function by printing the summary, as we have already done here. It's a very easy to read summary with all the formula. First and foremost, we have the model slot that covers all the settings to specify a model portfolio. This includes the type of portfolio, that is mean variance portfolio, the objective function to be optimized, which is risk minimization, min risk, the estimators for mean and covariance. Here we are by default using covariance estimator. and then some other optional parameters are there. One can easily modify the type of model portfolio that is to be constructed. For example, you can use this get type function. You can use this get type function and apply it to your default portfolio, default spec, and you can extract mean variance portfolio spec MV. You can change it. For example, let's say you want to change it to CBAR type. So you can use this set type argument, put your default spec and assign it a specification of CBAR, and now your specification are changed. Notice along with that your solver is also changed. We'll discuss more about the solver, but the idea here is that solver is changed to the relevant optimization portfolio. Now if you want to print this default spec, you can simply print it. You can print it and you can notice that now your type is CBAR. So we just changed the specification from a mean variance portfolio to a mean CBAR or conditional value at risk portfolio. For more discussion at CBAR, refer to the video topic on CBAR. Also notice that this model list entry provides the objective to be optimized, which is minimize risk, min risk. This list entry optimize in the model slot describes which objective function should be optimized. For example, one choice which is default is min risk, which minimizes the risk for a given target return. Then you have max return, which maximizes the risk return for a given target risk. And then you have objective risk function, which you can define a particular objective function. To put simply, the first two options, that is minimize risk or maximize return, are the most common choices. These are either minimizing the portfolio's risk for a given target return or maximizing the portfolio's return for a given target risk. In the default case of the mean variance portfolio, the target risk is calculated from the sample covariance. The target return is computed by the sample mean of the assets, if not otherwise specified. The third option leaves the user or somebody who is doing the programming with the possibility to define any other portfolio objective function. For example, one can maximize the Sharpe ratio. So for example, if you want to change the setting to optimize, you can type get optimize function. You can use this get optimize function and provide the argument of default spec. Let's see. Notice currently it is set to min risk. Now you can change it by putting it set optimize, and you can provide the default spec object, and you can change it to max return. You can run this, and now if I print my default spec object, notice now it is maximize return. Also, please notice the estimator slot in the model list. In Harry Markowitz mean variance portfolio model, the type MV, the default estimator is COV covariance estimator is employed, which computes the sample column means and the sample covariance matrix of the multivariate data series, such as we have been dealing in this lesson. There are a number of alternative estimators that will be discussed and also provided for by F portfolio functions such as Kendall's and Spearman's rank based covariance estimators, various robust estimators, a shrinkage and a backed estimator as well. We'll apply them wherever as may be required. Next, notice the portfolio slot. In the portfolio list slot, we have all the settings to specify the parameters for a portfolio. For example, you have target weights, target return and risk-free rate, number of frontier points, and the status of the solver. So for example, here you can see the solver is solve RGLPK. So you can use the extractor functions to retrieve the current settings in the portfolio slot and change those settings as we did earlier for the model slot. Three important arguments here are weights, which is a numeric vector of weight, target return, which is a numeric value of target return, and target risk, which is a numeric value of target risk. Now, for example, if the weights of a portfolio are given, then the target return and target risk are determined. They are no longer free. As a consequence, if you set the weights to a new value, then the target return and target risk are also changed to a new value. Similarly, if you change the values of target return and risk, the other two values are set to NA or they are determined. If all the three values are set to null, then it is assumed as an equal weight portfolio. In summary, if only one of the three values is different from null, then the following procedure will be started. For example, if the weights are specified, then it is assumed that a feasible portfolio should be considered. If the target return is specified, then it is assumed that the efficient portfolio with minimal risk should be considered. And if its risk is fixed, then the return should be maximized. Let's see this with one example. Currently, as we can see in the portfolio list, all the three arguments, target, weight, return, and risk, are set to null. Now let's set one of them. Let's set weights. Set weights of this default spec object. Since we have 7 objects, we can set it from 1 to, so we have sequence of 1 to 1, and we'll specify the length of 7. Let's have this sequence of 1 to 1, and we'll divide it by 7. We'll divide the sequence by 7. So we'll set the weights. We have this sequence. Let's print this. Inside this object we have 1, and we'll divide it by 7 to have equal weighted object 7. So now it has assigned equal weighted object. I can print this default spec. So it has equal weights. Notice that the target return, target risk are set to NA because we have specified the weights. So the return and risk objects are now fixed to NA. So basically we are telling portfolio to optimization to create a feasible portfolio with these equal weights. So the target return risk objects are fixed and they are set to NA. They will be determined in the optimization process. Similarly, if I set my target return, and let me set the target return of this default spec object to, let's say, 0.025, and let me print this default spec. Now that I have given the default returns, notice the other two objects, weights and target risk, are set to NA. So it will given this return, it will minimize the risk, and automatically the weights are automatically computed in the optimization process. Similarly, we can set the risk and then other two parameters, return and weights, are also determined the process. They are no longer variable, they are fixed by the optimization process. Next, you have risk-free rate. You can determine the risk-free rate using the extractor function. You can see the current risk-free rate and change the settings. You can also check the number of default frontier points. Currently the risk-free rate is set to 0 and number of frontier points to 50. These are often employed. Risk-free rate will be employed if you are constructing the tangency portfolio and computing Sharpe ratio. Number of frontier points will be required when you are constructing the efficient frontier. Lastly, you have optim slot or optim list, where you have the solver settings. The name of the solver to be used currently is set to solve RGLPK. Again, you have the extractor functions to see the current solver information or change it to some other solver. The name of the default solver used for the optimization of the mean variance Markowitz portfolio, which is the default portfolio, is the quadratic programming solver, which is named to solve R-quad programming. Since we change it to CBAR setting, we are seeing this as solve RGLPK. Let me again show it to you. If I change the set type of default spec to mean variance portfolio, it will be changed back. Notice the solver is changed back to solve quad programming again. A number of solvers are available with different parameters and different attributes depending upon the objective function, risk and return. To summarize, in this video, we initiated a simple portfolio object. We discussed in great detail the parameters including model list, which contain type of the portfolio function, the objective to be optimized, estimator, We also discussed the portfolio list slot where we discussed the weight, target return, target risk-free rate and number of frontier points. And lastly, we discussed the optim slot where we discussed the solver properties. In this video, we'll discuss how to set the portfolio constraints. Let's start with the simple portfolio specification object. Let's call it spec, SPEC. We can use the portfolio spec function to initiate this object. Once this object is initiated, let's start with the simple constraints, which is long constraints. Let's start with long constraints, long only. Now, many times we use only long constraint. That means we have all the long positions, no short positions. So let's define our default constraints as portfolio. Now we will use portfolio constraints function to specify our constraints. First, this is our return object that we are using, and we have initialized a portfolio spec, simple portfolio object with spec default configuration, and then we'll use our constraints which are long only. Let's assign this object and let's print the constraints. Notice in the constraints, notice when I run this default constraint object, notice the output. There is a lower value of 0 and upper value of 1. This is because the long only constraints assign lower and upper bounds for each asset between 0 and 1. 1 indicates 100%. So all the weights are allowed to vary between 0 and 1. One can also define short constraints. So instead of using long only constraints, I can use very similar setting and define my constraints as short only. Let's put it as short. And if I do that, so now I'll assign the short constraint and I'll run my default constraint object. Let me run this. So now if I run my default constraint object, notice now instead of 0 to 1, we have minus infinite to plus infinite. That is, there are no bounds because we have allowed unlimited short sale. So one can take any position on the negative or positive side in each of the assets individually. Next, we will discuss the box constraints. However, to make our portfolio object more appropriate, let me assign a target return to this, and most of the time we'll use long only conditions. So I'm running this long only condition, and in addition to that, I'm setting the target return, set target return as equal to set target return for this spec object equal to mean of final return. So the final ret object, mean of this object will be my final return, and these are my default constraints. So if I print my default constraint object, it will appear like this. Now we'll set a very interesting box constraint. Let's say I want my first box constraint to be that the minimum amount in each of the assets, the minimum weight in each of the assets from 1 to 3, asset number 1, 2 and 3 should be equal to minus 0.1. So this is the minimum weight that I want each of the asset to have. Then the second box constraint, I want from asset 4 to 7, asset number 4 to 7, the minimum amount I want is minus 0.2. Next, the maximum amount, let me first specify the remaining two conditions. So I'll use the box.3 third constraint, which is the maximum weight in asset 1 to 3 should be equal to 0.5, so it should not exceed by 0.5. Similarly, I'm assigning the last and final box constraint that my maximum weight, max weight should not exceed 0.8 from asset 4 to 7. So this is my box constraint that I have specified. Now let's set up my box constraint object, aggregate all these conditions. So let's my box constraint object, which is a combination of box.1, box.2, box.3 and box.4. So this is my combined box object. You can print it also. I can just print it separately. If I run it, I get all the box conditions. Now let me have my consolidated constraint object printed. So I'll use this portfolio constraint and I'll specify that I want my return object to be final rate. This is my return object that we have already discussed in previous set of videos on introduction and initiation of portfolio object. Then specification spec object, which is already there, and box constraint. Now if I print this object, notice the following interesting things. First and foremost, the lower limit, which is specified as for asset 1 to 3 minus 0.1, for asset 4 to 7, here notice for asset 4 to 7 minus 0.2, and the upper limit is 0.5 for asset 1 to 3 and 0.8 for asset 4 to 7. So these are our box constraints that we have specified. Next, we'll move to group constraint, where we can assign a condition which applies to a group of assets. How do we do that? So let's start with our first group constraint, group.1 equal to sum w, and I specify that asset number 1 and 3 should have a weight which is equal to 0.6. So 1 plus 3 should be equal to 0.6. This is my first constraint. Let us decide the second constraint, group.2, which is equal to min sum w equal to, now I'm specifying that asset, let's say 2 to 4 should have a minimum sum of 0.2. So 2 to 4 should have a minimum sum of 0.2, and group 3 that maximum sum for asset, let's say 5 to 7 should be equal to 0.8. So this is my last constraint. Let me combine all these constraints. So I can use this group constraints object and I can assign all the group constraints, group 1, group 2, group 3. So all these group constraints are assigned in this group constraint object. I can print this as well. So all 3 constraints are there. Now again, I can use the same portfolio constraint object, portfolio constraints object, where I need to specify my returns, asset having returns, then my portfolio object which I've already initialized, which is spec. Lastly, I'll provide my group constraints, and let's print this. So let us run all these commands and let me print this object. Notice what happens. So first, since this was a long object, so we have minimum and maximum limits 0 to 1, but now we have put group constraints. So let's interpret them. So first we specified the equal sum weight, which is 0.6 for security 1 and 3. So notice this equal sum 0.6, which is for security 1 Nifty and security 3 CSE. Similarly, we have minimum sum constraint as 0.2, which we can see lower matrix constraints here, 0.2 for security number 2 to 4. So 2, 3, 4 S&P, CSE and DAX. Lastly, we have maximum sum constraint, which is 0.8, which is applicable to security 5, 6 and 7. So these are our group constraints. Next, we'll also talk about risk budget constraints. So to assign budget constraints, let us have a look at simple example. I can have budget dot 1, which is my first budget constraint. And when I say budget constraint, this means risk budget constraint. So what is the contribution of each security to the risk of portfolio? So let us put first the minimum budget constraint, and I'll put 1 to n assets, which is my number of assets. In this case it is 7. So this n assets, and I specify the minimum as minus, maybe minus 2, and the maximum, this obviously pertains to on the lower side, budget 2, which I specify as max, the maximum risk contribution to the risk of the portfolio, max B, and I specify this as C1, so first asset, and then 2 to n assets. That means I want some combination for asset 1 and some combination for assets 2, and I specify this as C 0.5. This will be assigned to asset number 1, so 0.5 for asset number 1, and then I'll repeat from 0.6. Okay, instead of repeat, I'll just use a sequence. I'll use a sequence from 0.4 to 1 by 0.1. So it will assign an interesting sequence. And here instead of 1, I'll use just 1 to n assets. So all the assets will be assigned a sequence of 0.5, but since there are 7 assets, I'll use it as 0.4, and then I'll close the entire thing. So this is my risk budget constraint. Let me print this also. So let's decide or define a rather complete object as budget constraints, which is equal to C budget dot 1 comma budget dot 2. So these are my risk budgets for individual assets. Now if you want to print the complete thing, again we'll follow the same procedure. Budget constraints, I need to specify the return object, then the portfolio specification object that I have initialized already, and then budget constraints that we have already defined. So one small issue, although it's just a warning, but we need to have only 0.4 here, and I can remove this. So now this will work out fine. Now once I run this command, notice the budget constraint. So for example, the minimum constraint is -2, as we can see here for all the assets as I specified here, and the maximum budget constraint starts from 0.4 up to 1 for all the assets with an increment by 0.1. So this is my budget constraint. Now as a final thing, you would like to set up a very complex object which contains all these budget, group and individual box constraints, asset constraints. So let us see how it is done. So for that, I'll specify my constraints as a combination of box constraints, then group constraints, and lastly my budget constraints. This is my complete object. Finally, I will again use the same set of portfolio constraint function to create this object with very complex constraints, which is constraints, and if I print this, the complex object is produced. For example, these are the set of individual box constraints that are applied for each assets, maximum, up and minimum. Then you have group constraints, for example equal sum constraint that we discussed already. Here you have lower group constraint and upper group constraint that we have already discussed, and then you have risk budget bounds that we have discussed individually, -2 and then 0.4 to 1. So this is a very complex kind of object with very complex budget constraints for box, group and risk budget. To summarize this video, we introduced budget constraints and how to implement them in portfolio. We started with long and short portfolios where individual securities can be in the long or short, which is -infinity to +infinite, unlimited short sale. Then we introduced the individual asset constraints with box constraints, Next, we introduced group constraints for a group of assets. And lastly, we introduced budget constraints for risk budgets. And finally, we created a very complex portfolio object with complex constraints, which are a combination of box, group, and budget constraints.